Okay, we have 2 more chapters left, chapters 12 and 13. Chapter 12 is the last set of reading notes you will do. You're not going to do reading notes for chapter 13. Chapter 13 we will cover in a day. That's it. Your last assessment will cover both chapters 12 and 13. These 2 chapters cover more phantoms and panic. You might like this, you might not. Chapter 12, only phantoms. So no panics at all. It's only phantoms. What we are going to be looking at is specifically categorical data. We've looked at categorical data a little bit before with proportion. So 1 proportion inference and then 2 proportion inference. This is a continuation of that. So we are looking at more ways of analyzing categorical data. Sound good? Today we are going to do what's called a goodness of fit test. Goodness of fit. Okay, so here is where we're going to start. We are going to look at one example, just that's going to talk to us about the calculator, and then we will do a full phantoms example. Example number 1. We want to know, is the dice fair? So this shows a sample where the outcomes are 1 through 6, a normal dice. 13 times we got a 1, 23 times we got a 2, so on and so forth. Now, initially looking, if this die were fair, what would happen? What would be true? Okay, number of rolls would be equal for each of the outcomes. Now, we recognize, though, that real life, that's not practical, right? It's not going to be exactly equal. So, first thing that we're going to want to do is figure out how many times did we roll this dice. So I'm going to add up those numbers. Okay, and I'm going to tell you that there are 100 rolls total. So then what we would expect is that each number occurs 100 divided by 6 times. So that's 16.67. That's what we would expect for each outcome. You agree? Equally likely? Okay. So what I'm going to do is I'm going to show you on the calculator where to find this test and how to input the data, because it's a little bit different. This is one that has to be done on a calculator. So if you are someone who has not relied on your calculator very much before, that's okay, but this one has to be done on the calculator. Okay, so in this case, we get a p-value of 0.0427, about. So, do we think the dice is fair? No. No, we have evidence to believe the dice is not fair. Okay, so that's the calculator part. What I want you to recognize, like I said, this is called a chi-square goodness of fit test. Here's how you recognize this test. You have one categorical variable. With multiple possible outcomes. So our categorical variable in this case was the outcome when you roll a dice, and there were 6 different outcomes. If there were only 2, we could do a test for proportion. So let's say that we were flipping a coin 100 times. We could compare the proportion of heads to the proportion of tails. Or we could compare the proportion of heads to 0.5, which is what we would expect for a fair coin. You can't do that in this case, though, because you have too many categories to compare. Ela?
What's the context of the p-value in this problem?
Okay, a good question. The p-value, in this case, represents the probability of the outcomes we got or more extreme, assuming the dice is fair. Okay. This test is a little bit different than the other tests that you've done, so we really need to carry out a full test. But I wanted us to see how to use the calculator and why this is a goodness of fit test, how to recognize it. Okay. There is a table, a chi-square table. Is anybody here a big fan of using the table? Okay, so my question is anybody upset if we just skip the table? You don't ever have to use it. You okay if we skip it? Great. Okay, here is the full phantoms that we are going to do. Mendel's theory states that the number of a certain type of peas falling into the classification round and yellow, wrinkled and yellow, round and green, and wrinkled and green should be in the ratio of 9 to 3 to 3 to 1. Suppose that 100 such peas revealed 56, 19, 17, and 8 in their respective classes. Are the data consistent with the model? Okay. First of all, categorical data, because we have the classification of these peas. Second of all, there's multiple categories. There's 4 different categories. So hence, this is chi-square because it's categorical. Goodness of fit, it's only one variable. Okay. There are 4 different classifications we're looking at. Round and yellow, wrinkled and yellow, round and green, and wrinkled and green. Because there are 4 classifications, we need 4 different parameters. So I'm going to say let P1 be the population proportion of round and yellow peas. P2 is going to be the population proportion of wrinkled and yellow peas. P3 is the population proportion of round and green. P4, population proportion of wrinkled and green. Okay, so tedious, yes, I understand that. There's going to be some in your homework where you're going to have, I think there's one where you have 7 that you have to define. You don't need to write it out fully every time. I'm okay with that. But at least the first few. Okay, so next one. For your null, you need a value for each of those parameters. So your null, you're going to have P1 equals something, P2 equals something, P3 equals something, and P4 equals something. Okay, we are assuming that the P's are consistent with Mendel's theory. So Mendel's theory is that 9 to 3 to 3 to 1. That 9 to 3 to 3 to 1, if I add them all up, I get 16. So that means the proportion of round and yellow peas should be 9 out of 16. Wrinkled and yellow should be 3 out of 16, 3 out of 16, and 1 out of 16. And of course, those should sum to 1. So that is your null. Your alternative. Okay, so we have to be careful here. If the null is not true, that does not mean that all of these proportions are wrong. It does not mean that all of the proportions are wrong. It means at least one is wrong. So your alternative is going to be at least one of the above proportions is incorrect. So that's a nice thing with a goodness of fit test. That will always be your alternative. Always. First assumption, always. Sorry, Ela?
Is this always going to be in proportion?
Yes. Yeah, good question. This will always be proportion. First assumption, always. Random sample. In this case, it's going to be random sample. It doesn't change. So, do we have a random sample? We're not told that, so I'm going to say unsure, assume so. Okay, second assumption. Second assumption, we have to have a large sample. Here's what that means. All of the expected counts have to be greater than 5. Greater than 5. The way you calculate those expected counts is you take n and multiply by p. P coming from the null. So our n is the 100 p's. So I multiply that by 9 out of 16, and I get 56.25, which is greater than 5. Then I do my 3 out of 16, and that's 18.75. And then the 1 out of 16, and that is 6.25. So all are greater than 5. You don't need to do 3 out of 16 twice. There's no reason to write it twice. It's the same expected value. Good news, no 10% rule. Just these two assumptions. Questions before we keep going? Okay. For n, like I said, this is called a chi-square goodness of fit test. Alpha, we're going to use 0.05. Now, I haven't said this yet, and I probably should have said this earlier. Chi-square is a different kind of distribution. So we have a normal distribution, a t distribution, a chi-square distribution. So you're not going to say t or z. That doesn't make sense here because we're using chi-square. The other thing we have is degrees of freedom and tails. A chi-square test is always, every single time, upper-tailed. So this is upper-tailed. And it's going to have 3 degrees of freedom. Again, it's the number of categories minus 1, not n minus 1. So there are 4 kinds of p's. 4 minus 1 gives us the 3 degrees of freedom. So it is not 100 minus 1. Okay. Test statistic. It's going to be chi-square. What's really nice about this one is it is directly written on your formula sheet. Like the entire test statistic is. It is the sum. You're going to take the observed count, subtract the expected count, square it, and divide by the expected count. And then you will sum all of those up. So for our first category, I think we observed 56 P's. The expected was 56.25. We square it, we divide by 56.25. I expect you to do the first one and the last one. Can somebody tell me what the observed was on the last category? Is it 8? Yeah. So we have 8 minus 6.25 squared divided by 6.25. Again, you're not going to do that. You're going to let the calculator do it. At this point, we're going to go to the calculator. You're going to follow the exact same steps that you did before. So I want you to take a minute or two with the person next to you, put the observed values in a list, the expected values in a list, and go through the chi-square goodness of fit test. Agree. I got a test statistic of 0.66 about. Okay. So then we're going to draw a figure eventually. But remember, this is an upper-tailed test. So we're finding the probability that chi-square is greater or equal to that value. And that's about 0.88. Is that what you all got for the p-value? Okay. That's beautiful. Okay, so like I said, we are going to draw a figure, but I'm going to skip that for a minute. So in this case, 0.88 greater than 0.05. So we would fail to reject. So you might be asking yourself, or you should be asking yourself, how do I draw the figure? Right? How many people is that the favorite part? Your favorite part of the process? How many people is that your least favorite part of the process? You're going to love this. You ready? There's no way you have to do it by hand, or there's no way we know how to do it by hand. When you went and did the chi-square goodness of fit test on the calculator, did you notice the draw button?
Yes.
So what you're going to do is you're going to go to draw, and you are just going to copy the figure right off the calculator. Alice, you're just going to make up a figure.
Happy birthday, Alice.
You get to make one up for your birthday and forever.
Do you not get it?
That's a good question, Greta. What's yours?
I like
Me too. That was so good.
It's always like the perfect length.
Yeah.
I like
That one's like satisfying, I feel like. And it's like always easy.
Yeah.
Okay.
Everything else gets a little confusing. Yeah.
An A.
Hey, come back together. Come back together. I believe it looks something-ish like that.
Wait, mine didn't?
Okay. If your calculator gave you an error, you have something messed up somewhere else. So the two best things to check, go to y equals and make sure there's nothing in y equals, and make sure your stat plots are turned off. Off. So turn your stat plots off, clear out y equals, and try it again. And if you still get an error, let me know, and then I will troubleshoot for you.
You don't need to add any like 0.
You need to add a single label. The only label you need to add is your test statistic. Come on, that's going to save you guys, what, like 5 minutes on the test?
2.
It takes forever to load, though. Mine's still loading.
Well, so I will tell you, it's always going to be skewed right, Ela. So once you get the beginning part of it, you can fill in the rest. You just have to approximate what your skewed right distribution will look like. Any questions about this before we write a conclusion? Great. So, based on my analysis, I fail to reject the null. As there is insufficient evidence. Okay, before I keep writing. Remember, we assumed that the P's followed Mendel's theory. So the alternative then is that the P's don't follow Mendel's theory. So if I don't have enough evidence for the alternative, I don't have enough evidence that the P's do not follow Mendel's theory. As there's insufficient evidence that the P's do not follow Mendel's theory. I'm going to start my p-value all the way to the left since I have more room. 0.88 is the probability. Wording is going to change slightly here because of our calculations. So 0.88 is the probability of obtaining the observed distribution. Assuming the P's follow the ratio 9:3 to 3:1. Okay. What I would like to caution you with is this ratio business is the context, obviously. There's not always a ratio. So this is one where your wording is going to change slightly from problem to problem, but you're not going to say ratio every single time. You're going to have some problems where you're given a different context that's not a ratio. And so it wouldn't make sense to put a ratio into your answer. So you're going to have to follow the context of what you're given and what's being assumed. Questions? We have one other thing to talk about very, very briefly, and then those are our notes. Okay. This could come up in a multiple choice question, and it could ask you something like, if the chi-square value is 6.41 and there are 4 degrees of freedom, what's the p-value? So I want to make sure we know how to address that. If you go to second distribution, like you would for normal CDF and T-CDF, you're going to see there's a chi-square CDF. It works exactly the same as T-CDF. Lower bound, upper bound, degrees of freedom. Remember, for any chi-square test, it's always going to be upper-tailed. Always upper-tailed. So your lower bound would be 6.41. Your upper bound is 1 times 10 to the 99th, and you would have 4 degrees of freedom. So do that real quick, just to make sure you get the, well, you know where to find it, and that you get the right p-value. And you should get 0.17 as a p-value. So if you ever get a problem where it gives you the test statistic already, you're going to use chi-square CDF. And just keep in mind, it's an upper-tailed test.
There's going to be 4 degrees of freedom or 3?
I just made these numbers up.
Oh, okay.
So I made up, or I chose 4. Here's what I want you to do. In your packet, the next page is an AP problem. I don't want you to do that one. I want you to skip that one. And I want you to find this page. It has to do with criminologists, or that's what it starts with in the seasons, winter, spring, summer, and fall. I want you to do that problem. If you have time, the next page is not a full test. It just has some questions. So I want you to go between, at least do the first page, and if you can, go to the next one. You have, let's say 19 minutes with your group, maybe 15. and then we're going to go over whatever you get finished. Sound good? Okay, get started. If you have questions, please ask.